Hello, everyone. My name is Elena. My voice is a bit gone, so I'm sorry, but hopefully it'll be okay. So Fran just talked to us about the whole architecture, and he kept mentioning these proxies. And so I'm kind of here to tell you what exactly those proxies mean. And so the concept of proxies is really related to the concept of upgradability. So what is upgradability? And in the essence, upgradability is basically the ability to upgrade an already deployed smart contract. Because as we know, the blockchain is immutable. So once you deploy a smart contract, and let's say you wanted to add a feature or you discover a bug, it's actually impossible for you to upgrade your contract in like the canonical sense. We have to be a little bit more trickier and smarter about it. So as part of building Zeppelin OS, the Zeppelin team explored 3/4 proxy patterns. And when I kind of stumbled upon the repository, I kind of took a deep dive on what exactly they did. And I'm kind of here to tell you about their journey so you can understand exactly where they landed and their thought process behind it. So yeah, proxy patterns, what are those things? So this is the traditional approach. You have a client, like a web browser, or like your web app or dApp, and it's directly calling your logic contract, which is a smart contract deployed on Ethereum. And this is a proxy pattern. So now, instead of calling directly the logic contract, you go through a middleman, and that middleman is a proxy contract. And the important thing to know about this is it's possible because of two things. So there's something called a fallback function, meaning that if you call a function on a smart contract and that smart contract doesn't have that function, it can fall back to something else, to some other contract that it inherits or it can delegate call to. And another very important thing to note is that in this architecture, when you're calling a proxy contract that then delegate calls everything to a logic contract, it's the proxy contract storage that gets used. Meaning that later on, if we throw away the logic contract, we deprecate it, and we have a new one, it's the proxy contract that holds the storage, and we don't need to migrate all of the storage to a new version of the contract, because it's always been in the proxy contract that we're keeping forever. Okay, but if it's so great, why haven't we used it before? And there are a lot of really big concerns about using proxy patterns. And the biggest concern is that if you have one contract to hold the storage, but another contract that has all the logic, then the logic contract can actually accidentally overwrite some of the memory that the first contract might need. So there's like all these concerns about memory corruption, and you have to be really careful about how you think about memory allocation when you're writing this architecture. Okay, so this is the basics of a proxy pattern. So what Zeppelin did is there's something called delegate call that actually comes with Solidity. It's a wrapped function around a delegate call opcode. But that's not good enough because that method doesn't return the data that comes back from our logic contract. So we actually have a pattern where we call a proxy contract, the proxy contract calls the logic contract, and then the actual return data goes back to the client. So from the client's perspective, everything goes as usual. And this is inherited storage. Inherited storage has actually been around for a long time, and basically it works like this. The proxy contract and the logic contract both inherit from another contract called upgradability storage. So an upgradability storage has all the state variables that are needed for upgradability. So for example, all it needs right now is to point to an address for where the logic contract actually lives. And it looks kind of like this. So when you write your logic contract or your token contract, it needs to inherit from something called upgradable. And when you write your proxy contract, it's going to inherit from upgradability storage. And upgradability storage, basically all it does is an upgradable, all it has, for example, is one state variable that's needed for upgradability, which is the address of where the implementation logic contract is. And the reason why this is important is because So yeah, this pattern is often called simple storage. So if you've seen that online somewhere, this is basically what it's referring to. And it's a pretty old concept. So the first implementation that I've seen was actually over 2 years ago. So this is nothing new. It's just that people are kind of a little bit afraid of using it. So the takeaway is that it's a simple approach, and future logic contracts have to inherit from the first one, which makes sense because you don't want to introduce different mappings because that'll lead to memory corruption. And it allows you to introduce new state variables in the future. But the biggest downside is you have to write your logic contract in a way that it's aware that it's in this proxy architecture. Meaning that when you write your logic contract, it has to inherit from this upgradability contract, which has the state variable to keep track of its own address. So when you're writing a logic contract, that doesn't actually make a lot of sense. So then Steph and team, okay, I thought, okay, maybe we can think harder and think of something better. And so the second one is eternal storage. So this is, once again, a familiar view. We have a middleman, it calls logic contract. And then it kind of looks like this. And this is a bit scary, but it's a pretty simple concept. So now we say, okay, in our logic contract, we might have some mappings, we might have some variables, and we're going to extract all of that into a separate contract called eternal storage. And the proxy is not going to be aware of all the state variables. So this kind of condenses down to something like this. So the logic contract inherits from eternal storage, which has all the mappings that we might ever need, even for future contracts. And the proxy also inherits this format. So now the proxy knows, is aware of its own state variables. So the proxy now can have like a state variable to keep track of where the logic contract lives. And it has all this. And because the proxy contract is now aware of all the state variables that are needed both for the proxy and the logic, there's no chance of memory corruption. So that's basically the takeaways. It's an intuitive approach because you're extracting everything that's associated with storage to one contract. But the biggest downfall is that when you write your logic contract, you have to be mindful of extracting every state variable into the separate contract, meaning that you wanted to add a uint. Now you have to write it into this other contract, which is kind of unintuitive. And once again, the biggest downfall is that you have to write your logic contract in such a way that it's aware that it's in this proxy architecture, which isn't good enough. So then it comes the third and sort of final approach, which is unstructured storage. And this is really cool. And it looks kind of like this. So now it's a bit simpler. The takeaway here is that the proxy now has owned upgradability storage, meaning that it has got a separate contract to keep track of who the proxy owner is, and then it has another contract that keeps track of where the logic contract address is. And so it looks kind of like this. So for example, now it doesn't need to store any state variables. It stores a constant variable. And a constant variable isn't stored in storage. It actually is stored with the contract code. So all of this doesn't get saved in storage. And this constant is just a string that is hashed. So for example, we hash the string proxy owner. And likewise for the implementation position. And this actually becomes the position for where we load that particular value. Meaning that in memory, we're basically making up a position to load the value of where the logic contract address is. And it's kind of a weird approach to get around. But basically what happens is when we want to get the implementation, meaning we want to get the address of where the logic contract is, we first find the position in memory for where we need to look. And so we get position equals implementation position. And implementation position is, once again, a hash of a string. And then we use an opcode to load a word size, and a word size is 32 bytes, to get where the implementation address is. An implementation address, an address is length of 32 bytes. So it gets that word size. And likewise, for steady implementation, you keep that same constant position, and then you store a new value in that constant position, and likewise for an owner. So in a way, it's kind of like a treasure map. So where you keep the treasure is constant, and you even have a map for it, but you can dig up your treasure trunk and put a different value in it, but the location of where that treasure is always constant. So then the biggest question is, okay, is it safe? Because if anyone have ever programmed in C, this is basically how you get seg faults. you just choose a random memory allocation, and that's how you basically get into trouble. So here's a quick kind of lesson of how storage and Solidity works. So we have statically sized variables, and those are uints and bytes and so on. And those are laid out contiguously in memory, meaning that they start from position 0, and then it just goes in a contiguous way and fills up all those memory slots. Mappings and dynamically sized variables are trickier because they start in a very similar fashion. So once again, the next available slot is when they start, but the values are stored in a much trickier way. So for example, if you have a mapping, the mapping might start at position P, but if you want to store a variable, like a variable K, then we're actually going to hash the concatenation of K and P. And basically, in Solidity, they're taking a bet that that is a random enough location that there won't be any hash collision, and it's safe to store a value there. And so some of you are thinking, wait, hashing some value is going to give you a really big number. Is it possible that a smart contract is going to have that much memory? Because once again, if you're familiar with programming in C, your program has very limited storage, and you're not allowed to just do that. So here's a cool thing about how Solidity works. You actually have access to almost infinite memory. You have access to 2 to the 256-bit virtual address space, which is pretty incredible because it's probably one of the few cases where you actually have a true O1, so constant lookup for maps, for like key value stores. And that's because you have such infinite space and everything is so sparse that there's basically no hash collision ever. And basically the point here is if Solidity itself doesn't care about hash collision because they're confident that if they ever hash such a value, then it's actually kind of safe to assume the same thing. So back to the problem at hand, we're trying to figure out whether or not there's ever a hash collision here. If there's ever a mapping that could potentially overwrite that treasure that we're trying to place in a random location. And that could only ever happen is if we ever hash a value of a mapping concatenated with the initial position of the mapping, that it would equal that string that's more than 32 bytes. And that is pretty highly unlikely. So the TLDR of this is we think it's pretty safe. And so the cool thing about this is now finally we have a solution where you can write your logic contract such that it is not aware at all that it is a part of a proxy pattern architecture. And that's pretty cool. So this is like a 3.1 a proxy pattern. And it fixes something called a function collision. So for example, let's say the proxy has a function only owner, which is a pretty reasonable thing to have, and the logic contract that it references also has only owner. So how do you distinguish which function should be caught and when? And so basically, there's a workaround, and you're checking who the sender is. And if the sender is the admin or the proxy owner, then it calls the functions in the proxy. Otherwise, it falls back to the logic contract. Isn't this amazing? And that's pretty much it. And so that's kind of the journey that Zeppelin took. And I thought it was pretty fascinating, so I wanted to share it with you guys too. But yeah, it's very cool to see what they're going to come up with next. So, and that's it. Thank you.